SAE310S is a stainless steel metal used for high temperature application. It is produced because it is very resistant to corrosion by high temperature gases. The high chromium and nickel content give the steel excellent oxidation resistance as well as high strength at high temperature. SAE310S should contain 25% chromium and 20% nickel. A company that produces these cylinders is under surveillance of the Safety Authority. This Safety Authority checks two requirements for the produced cylinders. First of all, 100% of the cylinders should have a chromium percentage between 24.055 and 25.99 and a nickel percentage between 18.41 and 21.65. Furthermore, 95% of the cylinders should have a chromium percentage between 24.10 and 25.90 and a nickel percentage between 18.50 and 21.50. Every time one of those requirements is violated, the company needs to pay a fine of 1 million euros. The company produces about 1,000 cylinders per day for 10 consecutive days. They want to predict whether they are going to get a fine, so they came up with two different methods to test the percentages, the destructive test and the non-destructive test. For the destructive test, 10 cylinders are checked each day. Each of the cylinders is divided into 5 layers. Each layer is then divided into 80 cells. Each cell is assigned an X, Y and Z coordinate from which the location within the cylinder can be determined. The company then checked 20 randomly selected cells per cylinder to test the real percentages of chromium and nickel. For the non-destructive test, the cylinders are divided into cells in the same way as for the destructive test. Now 10 cells from the top layer and 10 cells from the bottom layer are tested for their percentages of chromium and nickel. After these 10 days, the Safety Authority randomly selects 100 cylinders. Then for each cylinder they randomly select 10 cells and test them to see if the requirements were violated. We received the tested data from the company and were asked if we could calculate the expected fine for the future based on the given data. First, we found it interesting to see which cylinders were closest to violating the requirements. From this study we found out that the highest and lowest percentages of both metals are concentrated at certain places. High percentages of chromium were found at the bottom right in the middle, while the lowest chromium percentages were found at the bottom left in the middle. For nickel, high percentages were found at the top right in the middle. The lowest percentages were found in the top left in the middle. Since chromium is lighter than nickel, we concluded that the cylinders are dried in an upside-down skew position, so that the light metals rise to the top and the heavy metals to the bottom. The skewness explains that the heavier higher nickel and chromium percentages ended up on the left, and the lighter lower percentages ended up on the right. Of course, the most important question is, can we predict the expected fine the company has to pay? In order to calculate this, we had to apply linear regression to the data. We wrote a program that uses 80% of the data to fit a suitable model. Then the other 20% of the data is predicted by the model and compared to the real data to see how accurate our prediction was. There were multiple partitions made to make the model as accurate as possible. This final model gives the expected percentage of both metals in that particular cell, but it also gives an interval for which the model is 90% sure the percentage should lie within. From this model, we concluded that, based on the given data, the expected fine the company will have to pay is 203 million euros.